Hi all, welcome to new class. Today's class is the continuation of applications of op-amp. So, in the previous class, we have discussed about some applications of op-amps. So, there are some more applications. Let us discuss about that. Next is half-wave rectifier using op-amp. And there are two types of half-wave rectifier using op-amp. One is non-inverting and the other is inverting half-wave rectifier. So let us discuss about non-inverting half-wave rectifier using op-amp. So this is the circuit diagram for the non-inverting half-wave rectifier. The op-amps can enhance the performance of the diode circuits. An op-amp eliminates the effect of diode voltage drop, allowing us to rectify, peak detect, then clip and clamp low level signals. So here this is the circuit for the active half-wave rectifier circuit. When the input signal goes positive, so this is non-inverting, so the input is given to the non-inverting terminal. So when the input signal goes positive, the output goes positive and it turns on the diode. The circuit then acts as like a voltage follower and the positive half cycle appears across the load resistor. So during the positive half cycle, what will be the output? It will be also the positive half cycle of the input signal. And on the other hand, when the input goes negative, the op-amp goes, that is the op-amp output goes negative. So it turns off the diode. So here this diode will be open. So no voltage appears across the load resistor. So here during the negative half cycle there will be no output. Again during the positive half cycle we will get the output like this. So this is about the non-inverting half-wave rectifier using op-amp. Next is inverting half-wave rectifier. So this is the circuit diagram for the inverting half-wave rectifier. So it consists of two diodes. And here the input signal is applied at the inverting terminal. So when V in is positive, then what happens? V0 will be negative. So V0 will be negative here. Then which diode will be conducting? So when V0 is negative, diode D1 gets forward biased. So D2 will be reverse biased. So what will be the output? So this is input waveform. So diode D1 conducts. That is here positive signal is applied. Then output is negative. Then D1 conducts. So B1. So we will get the output here. That is output is negative. So it will be like this. So during the positive half cycle, we will get output at this terminal. Then when V in is negative, then V0 will be positive. So V0 positive means diode D2 forward biased and D1 reverse biased. So we will get the output here. That is negative input, output is positive. So diode D2 conducts. So we will get the output here, that is it will be like this. Again in the next half cycle it will be like this, again here like this. So if a sinusoidal wave is applied at the input, the output V2 gives positive going ripples and V1 gives the negative going ripples. So this is inverting half wave rectifier using op-amp. Next is full wave rectifier. So this is the circuit diagram for the full wave rectifier. It consists of two op-amps. Both A1 and A2 act as inverter and also two diodes. So when V in is positive, that is during the positive half cycle of V in, what happens? The output of A1 will be negative. So when V in is positive, output of A1 will be negative. Then which diode conducts? So diode D1 conducts and D2 is in the reverse biased condition. So this negative half cycle appears at the input of A2. So what will be the output? So the output becomes positive. So here the output waveform will be positive. So that is the positive half cycle. Then during the negative half cycle, the output of A1 will be positive. Then D2 conducts and D1 is in the off position. So diode D2 conducts and the positive half cycle appears at the input of A2. So what will be the output? The output will be positive because this is non-inverting terminal. So this is positive. Then the cycle repeats. So this is about the full wave rectifier using op-amp. Next is comparators. A comparator is a circuit which compares a signal voltage applied at one input of an op-amp with a non-reference voltage at the other input. So a comparator is a circuit which compares a signal voltage applied at one input of an op-amp with a non-reference voltage at the other input. And it is basically open loop op-amp with output voltage plus or minus Vsat, that is the saturation voltage. And this is the case of ideal comparator. That is, this is ideal comparator transfer cara, and this is the commercial or practical comparator transfer cara. And there are two types of comparators, non-inverting comparator and inverting comparator. So let us study about non-inverting comparator.
So next is non-inverting comparator, and this is the circuit diagram for the non-inverting comparator.
Here, a fixed reference voltage V reference is applied to the negative input terminal of the op-amp, and a time varying signal V in is applied to the positive input, and the output voltage is at minus Vsat for V in is, this V in is less than V reference, and plus Vsat for V in is greater than V reference. That is, here If V in is less than V reference, that is V in, this is input voltage. If it is less than, this is V reference. So if it is less than this V reference, and hence output will be minus V sat. So minus V sat means it will be here. So this is minus V sat. So the output will be here. And V0 goes to positive V sat when V in is greater than V reference. That is, when this V in is greater than this voltage, then it goes to positive V sat. So this is plus V sat. So it goes to positive V sat when V in is greater than this reference voltage. So it will be like this. So the output will be like this. That is, again here V in is less than this V reference. So here it goes to the negative saturation. So here also, then again here it goes to the positive saturation. So this is the output for positive reference voltage. That is, if the reference voltage is positive, then the output will be like this. That is, if this is positive, then when V in is less than this V reference, then it goes to the negative saturation. And also when V in is greater than this V reference, then it goes to the positive saturation voltage. So this is the input and output for negative reference voltage. That is, if the reference voltage is negative, then what happens? Minus V sat when V in is less than V reference, and positive V sat when V in is greater than V reference. So this is V reference, and here this is V in. So this is greater than this V reference. So what happens? It is positive saturation. So up to this point, it is positive saturation voltage. And when V in is less than V reference, that is, this is reference voltage. So it is less than means this is the value which is less than V reference. So it will be minus V sat. That is, up to this point it will be minus V sat, then again positive V sat. So this is the case for negative reference voltage, and this is for the positive reference voltage. That is, here this is positive reference voltage. If V in is, this is V in, it is less than V reference means it is negative saturation, and if this V in is greater than this reference voltage, it is positive V saturation. So this is about the non-inverting comparator. Next is zero crossing detector. So this is the circuit diagram for the zero crossing detector. So it is a comparator that switches the output from off to on when input crosses the zero reference voltage. That is, zero crossing detector is a comparator that switches the output from off to on when the input crosses the zero reference voltage. Here the output is driven into negative saturation when the input signal passes through the 0 in the positive direction. That is, here the output goes to the negative saturation. That is, negative Vsat when the input signal, that is when the input signal passes through the 0 in the positive direction. So here it will be negative saturation. So here this is the input signal passes through the 0 in the positive direction. So it will be negative saturation. And when the input signal passes through the 0 in the negative direction, the output switches the positive saturation. That is, when the input signal passes through the 0 in the negative direction, the output switches and saturate positively. So this is plus Vsat and this is negative Vsat. So here we will get the output like this. So this circuit can be used as an easy technique to check whether the op-amp is in good condition. So that is about the zero crossing detector. Next is Schmitt trigger. So this is the circuit diagram for the Schmitt trigger and it is merely a comparator with a positive feedback. So the comparator is open loop op-amp. Then here this is a comparator with a positive feedback. And this circuit converts irregular shaped waveform to square wave or pulse. So it is also known as squaring circuit. So here the input voltage is applied to the negative input terminal and the feedback voltage is applied to the positive input terminal. The input voltage triggers the output V0 every time it exceeds certain voltage levels. And these voltage levels are called upper threshold voltage VUT and lower threshold voltage VLT. That is, the input voltage triggers the output voltage V0 every time it exceeds the upper threshold voltage or lower threshold voltage. And these threshold voltages are obtained by the voltage divider R1 and R2. Let this point be the upper threshold voltage and this point be the lower threshold voltage. Suppose the output voltage is equal to plus Vsat. So the output voltage is plus Vsat. Then the voltage at the input terminal will be VUT, that is the upper threshold voltage is equal to output voltage, that is plus Vsat into the resistance through that branch, that is R2 divided by total resistance is R1 plus R2. So this is upper threshold voltage and which is applied to the positive input terminal. As long as V in, so this is the input voltage. So as long as V in is less than upper threshold voltage. So here this is positive Vsat. So the first case is plus Vsat. So as long as the input voltage is less than upper threshold voltage, the output remains constant at plus Vsat. And when the input is just greater than the PUT, that is upper threshold voltage, the output switches to minus Vsat. So this is minus Vsat. So when the input is greater than VUT, it switches to negative saturation voltage and remains at this level as long as Vin is greater than VUT. So it remains at this point as long as Vin is greater than VUT. Next case is when here now this output voltage is minus V saturation, then it is applied at the positive terminal. So what will be the positive terminal voltage? That is VLT is equal to minus V saturation into R2 divided by R1 plus R2. So this is the lower threshold voltage. And the input voltage Vin must be lesser than VLT in order to cause V0 to switch from minus saturation to plus saturation. That is, the input voltage Vin must be lesser than this VLT. So, this is VLT. V in less than, that means it is this portion. So, up to this one it will be minus Vsat. So, the input voltage V in must be less than the VLT in order to cause the output voltage V0 to switch from the minus Vsat to plus Vsat. Again, it will be like this. That is, the cycle continues like this. That is, when Vin is greater than VUT, the output goes from plus Vsat to minus Vsat. And when Vin, that is the input voltage, is less than VLT, the output goes from minus Vsat to plus Vsat. So this is about the Schmitt trigger. So that is about the applications of op-amp. There are some more applications of op-amp like clipping circuits, clamping circuits, then peak detector, instrumentation amplifier, then sawtooth wave generation, triangular wave generation, then beam bridge oscillator, like that. So here we are discussed about some of applications of op-amps. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.